Welcome to my talk for MEDI 2021. I am Pascal André from the University of Nantes, and I will present a still ongoing work led with Mohamed Tebib on the more automation in model-driven development. Let's start by some key value findings on the software development cost. IT is expensive. Gartner forecasted a cost of $4.1 trillion in 2021. Software development represents the main part of it, and especially its human resource cost. Last but not least, the low quality represents a significant part of the IT cost, which makes IT the unique engineering field where leaving bugs makes money. So the question is, should we pay so much for poor quality? Model-driven development can help to improve the situation because abstraction enables to reason at the model level before automating implementation. Our context is models. Model-based development or engineering is a software development approach that uses models before implementing. More precisely, our context is model-driven development where model transformation are central to the development process and produce software from the models. MTA is a OMGI, particular vision of MDD, and model-driven engineering is this broader field, including model evolution, reverse engineering, language engineering, and so on. As we will show later, one problem is that model refinement miss automation. In this paper, our contribution is to rationalize the process by structuring frame to increase the role of platform in model transformation. This presentation is organized in 3 steps. In step 1, we overview MDD practice and issues, for which we propose a structuring frame in step 2. Step 3 will discuss about implementation issues and validation. Then I will conclude. There are 3 approaches to get code from models. Standard approach with implementation with design and programming activities. Code generation from high-level specification using case tools, or model transformation with a refinement process. They represent different degrees of automation. We experimented them on a representative small case study. It is a simple home automation example, a garage door with motor here, sensors, and controlled by a remote transmitter. We are interested in the software part, for which we provided a logic model described with UML. This model is a result of the analysis stage, which represents the left part of the Y process here. The right part in green represents the technical environment, which includes here LEGO EV3 robots running on the Lejos Java framework and Android for the remote control. During the manual development, we have to design the solution and gradually immerse the analysis model here into the technical platform in the spirit of the Y development cycle. The students implemented programs and a mock-up to test it. So you can see here the Lego prototype and here the Android application. The operation results was a running application, but the logic model was rather a reference instead of an abstraction. The functional capability overrides over software qualities for students. It means the program should work. Of course, the knowledge and the expertise influences the design and implementation decision to be taken. We also note that communication refinement is a first-class issue to deal with in such application. The question is how to automate the development on year after the maintenance. One possible answer is code generation. We can quickly compare here the code generation of different case tools, and the table is a smart example of it. The coverage is quite good for the structure, but low for the behavior. Here, behavior means state transition diagram and operation definition, but also the message, which we call here message-oriented middleware. The integration with annotation and road trip exists in some tools, but not for the API mapping, which binds design concepts to implementation frameworks. None of them implement it. Note that the code generator can be used for simulation purpose or here to build the target code. The result is often disappointing. We note here 20%, especially for the behavioral and communication parts. Thus, stepwise refinement is necessary. This is the third way with model transformation. We experimented model transformation, but again, we face difficulties. There are no generic transformation model, and people design empirically their meta models on transformation. There's a weak engineering tool support. There exist languages and transformation tooling, but engineering is still challenging. Most transformations are complex. We experimented, and it was difficult to write the transformation when the source and target model are not semantically closed. This is the case here for state charts or communications. Again, it is not easy to insert design decision in systematic transformation and to provide parameters. Last, design macro and micro transformation implies to rationalize the transformation process, which requires trial and error. And here, students tend to write teeny ATL transformation instead of big transformation. All these make it difficult to apply in practice. Next, we discuss some key issues for automation. MDD must solve the problem of the distance between the logic model and the technical platform. Only detailed models can lead to detailed code, so you must have enough information, especially for simulation. Design concerns cover cross-cutting concepts, persistence, guide, distribution, and communication that imply human decision and that may have impact to each other. Again, we said there are no generic transformation process with guidelines and flexibility enough to customize the transformation. As an answer, we propose a structuring frame where reverse engineering the technical framework to make it closer to the abstractions. We call it PDM, Platform Dependent Model. The quality of input models must be checked before transformation to avoid useless work. A stepwise refinement handles the design concerns according to their impact. And last, the steps must be precisely defined in order to make automation for the transformation. In that new vision, software development from models is also an adaptation problem that maps model entities to framework entities. Reverse engineering frameworks enable to build platform-dependent models needed in that refinement mapping. Note also that we consider everything as a model until the code generation. This vision leads to a macro transformation architecture with 4 levels: deployment model, a component model, an object-oriented programming model, and the last program level. We have to build the abstraction here in blue, corresponding to each model to map. Now, I will overview the first milestones of implementation and validation. We currently define systematic transformation for T2, T3, and T4, and provided guidelines for T1. We experimented model transformation for UML state machine to Java using ATL and Java code generation using Papyrus. We also worked on PDM abstraction to reverse engineering here the Legos library using Modisco and AGLG in order to implement a PDM adaptation using the adapter pattern to connect AOP models to PDM. Last, we defined communication primitives to overpass the problem of message send in network communication like Bluetooth or Wi-Fi. Details are available in the paper and its web appendix. Time is to conclude. In summary, automated model-driven development is required for what I could call low-cost development for software and maintenance. But the problem remains thorny due to the variety of paradigms, domains, frameworks, development practice, the fact that the tool support is not mature enough to provide transformation on the shelf. So we proposed a generic process of 4 macro transformation with systematic definition for these transformation and the separation of design concerns, just like your chip plug on an integrated secret slot. Second, the use of PDM abstraction already provided or obtained by reverse engineering make it possible to join the logic and platform point of view. As we implemented micro transformation, maybe 5% of all what is necessary here, related to UML refinement and PDM abstraction. Of course, the current contribution remains limited. There are open issues on high-level abstraction and transformation that impact the parallelism in the lower level. We must identify the automated and manual activities, for example, the graphic user interface, and the applicability, scope, and scalability is not fully clear yet. This is still empirical. The overall approach requires directories of platform-dependent model that could be given by framework providers as a kind of operational user manual. Also, we need transformation on the shelf that could be given by transformation provider in order to build the transformation processes. Their midterm perspective are to continue to explore the abstraction of the framework here, the Leros framework, the implementation of the lowest layer T4 with the communication abstractions, and applies the whole process to the case study. This is still ongoing. This is an ambitious project and contributions are welcome because there are many things to do. Thank you for your attention. We may have answer to some questions.